Okay, our next speaker is Maria, and she will speak on B-spline regularization and the modeling look at B-splines.
Well, thank you so much. I have to tell you that I'm going to disappoint everyone here today, okay? I'm going to disappoint the mathematicians because I have hardly any mathematics. And I'm going to disappoint the statisticians because I'm going to talk about very more or less basic things. If you are in the world of non-parametric regression, you will know everything. But what I want to give the people who are not so familiar with the modeling side of spline is an idea of what you can do with penalties. Okay, so that's my aim today. No me pasa. Okay. Okay. So the idea is that I am in a context in which the aim is not approximate a function. It's approximate something I don't know what it is. Okay? Because I observe some data, and first the data comes with noise. Okay? And second, the function I want to estimate, it will be maybe the sum of many different functions. I really don't know what I am approximating. Maybe this is very uncomfortable for some people, but this is what we deal in real life every day if we analyze data, okay? So what we observe is the sum of something that has a structure plus some variability that may be due to many different sources, okay? But when I see the data, I don't know which part is which, okay? So my aim is to separate these two things, okay? So of course, you know, depends on what I do. This separation could be something very different, okay? The blue line and the red line are very different, okay? So how do I know what the truth is? Well, we don't know. We just hope that I get it right and I attach some probability to it, okay? So that's the idea of the modeling, okay? So I want to give you some basic references of what I'm going to talk about, which are penalized splines. So there is a very nice book written by Paul Eilers and Brian Marks, who are the people who first introduced P-splines. This year is 30 years ago. It was in 1996, which is the reference at the top. Okay, and then 10 years ago, I was really honored to be invited to write a review paper on 20 years of P-splines. So if you want to go a bit deeper on what this is, these are, you know, very, very nice, practically oriented references, okay? Okay, so a model determines what we interpret as a signal. We have to have some, either we have prior knowledge or we assume something, okay? In my context, I'm going to assume some degree of smoothness, okay? Otherwise, you don't use these techniques, okay? If you have a time series, you are doing something else, okay? So there is an assumption behind what I'm going to do, okay? So this is my basic model, okay? Alex showed it before. I have some observations, and I assume I can decompose this in two parts, some unknown function plus an error. If I don't need to say anything about the error, if I don't want to do any inference, if I don't bother about the error, I don't have to assume anything. But in my context, in general, you assume something because you want to give an uncertainty to your estimated function, okay? So that goes with assuming something about the error, okay? So of course, what do we do? Well, we are going to use representation for the function, okay? And we are going to use some type of basis, thin plate spline, B-splines, cubic spline, whatever you want to use as a basis. Very important thing for us is that the bases have local support. Why is this important? Because that is going to help me to adapt to what is going on in the data, okay? So if a basis is evaluated in the whole grid of data points, a little change on one side will affect what is going on the other side. So being local is important, okay? And why low rank smoothers? Alex talked about smoothing spline. Smoothing splines are okay if you have 1,000 data points. Nowadays, you never ever have 1,000 data points. You have 100,000 data points. If you put a knot per observation, there is no way that you can solve your problem, okay? So we go to low rank smoothers. Smoothers which uses far less knots than observations. Of course, this comes with problems attached that I'm going to talk about in a minute, okay? So we have like two extreme cases. I have as many knots as data points, and I use a penalty to control the smoothness, or I choose the location and position, how many knots, and I control the shape with that. But in the middle are penalized splines, because we use low rank smoothers, less knots and observations, but we put a penalty, so the position of the knots is not relevant anymore, okay? And this is what I'm going to talk about. So I'm not going to say very much about B-splines because we have been listening to this all this week, but I want to talk about something. There is not a unique way to define B-splines, okay? In general, B-splines in many places are defined as clumped at the edge. Knots are repeated at the edge. For me, this is not good, okay? Well, in my situation, it's not good, and I'm going to say why. First, because when you do tensor products of those splines, behavior becomes weird, but also because for me, in the way how I work, it's important that they are invariant to translation, okay? So that the basis is exactly the same all over the place, okay? So what do I do to get this? I also use knots outside the range, okay, outside the range of my covariate, okay? Then I can define uniform B-splines, okay? As I said, this is the opposite as the usual definition in which you repeat the knots at the end. Why is also important for my applications to do this? Because sometimes I'm using B-splines in the context of time series. So I need to forecast in the future. If I stop my spline at the edge, there is no way. Imagine that my X is time, and I want to forecast what is going, what the smooth trend is in the future. Unless I'm allow the B-spline to continue, I cannot do this, okay? So these are one of the reasons why I prefer, and in general, in my environment, we prefer these uniform B-splines, okay? So once you have your basis, you give some weights, to the B-spline basis, and depending on the weight, okay, you get different shapes, okay? That's what you do. Of course, the key point is how do you choose these weights, okay? So you can use least squares, okay? Basic thing, okay? Your B-spline basis evaluated in your observations become a matrix, a known matrix B, and you have some coefficients A attached to it, so you use least squares. But of course, yeah, to control the shape, as I said, you can do two things. Either select the knots, where they are and how many, or you control it through some sort of penalization, okay? So these are the two extremes. So what I have done here, this plot is just, I'm changing the number of bases. And as you change the number of bases, the shape of the function changes. Okay, so that's one way to do it. Yeah. Problem. And it's difficult. It's not a simple problem to decide how many knots and where to put them. Okay. I'm going to talk about in a minute about recent work, beautiful work, very fast way to do this. Okay. But this is not my goal. I'm going to go through the penalty bit. Why? Because I want to show you that the penalties can do a lot of things for you, okay? So flexibility depends on location and position of the knots. And I want to point out this paper, Spline Regression with Automatic Knot Selection. It's a beautiful paper in which the knot selection become a penalized regression problem, okay? So it's done assuming an L0 norm. So in fact, what you are saying is that you want to send to zero the coefficient or not. That implies choosing the knot. This norm can be approximated by a quadratic penalty, so everything falls in a very, standard regression problem. This has been done in one dimension for one function. I'm working at the moment with a student. We have extended this to the generalized additive model when you have more than one smooth function. And we are also working on how to extend this to multidimensional. But as I said, it's very, very fast and it's really, really, really beautiful. But I'm going to go to the alternative approach. So, which is what P-splines are about. P-splines are penalized splines, okay? Although I'm working here with B-spline basis, as I said, you just need a low rank smoother, whatever you want to use, and quadratic penalties. So you choose a sufficiently large basis. What is sufficiently large? Okay. If you are in one dimension, okay, one knot per every 5 points, but no more than 40. Unless your data are really weird, okay, you don't need that many knots, With 40 knots in general, you are okay. When you are in a multidimensional, okay, less than 100 knots is, you are not going to account for these things correctly, but sufficiently large. And then you control the shape by controlling the acceleration of your curve, the second derivative, okay? So second derivative, because your function is represented as the product of B-spline basis and coefficients, the second derivative, okay, becomes, the integral of the second derivative becomes the integral of the second derivative of a B-spline. The second derivative of a B-spline is something very easy to calculate because of the recursive, okay, way to calculate a B-spline. So this is in principle not a problem. Okay, so you get this penalized. Usually you have seen this many, many times. So you get a closed form for your coefficients. Okay, so you are set to go. Of course, we have the problem of lambda. I will talk about a bit later on how to choose lambda in a very fast way. Okay, but okay, and this is the idea of penalized splines. We are going to do the modeling not on the function, but on the coefficients attached to the function, okay? So instead of assuming that the acceleration, has to be controlled, what we are going to assume is that the value of two consecutive coefficients, okay, cannot be very far. Two consecutive coefficients, if the coefficients, the magnitude of two coefficients next to each other. Why do I talk about next to each other? Because you have a sequence of nodes, you have a sequence of coefficients. If two coefficients that are next to each other are similar in magnitude, the function will change very little. If the magnitude is very large, the difference, then they will change a lot. So instead of working with the second derivative of the function, I'm working with the second order differences between coefficients. It's like a surrogate problem, okay? But this is much faster, okay, to calculate. If you want to stick to the second derivative, it doesn't matter, okay? Because now you can calculate it very, very quickly. But this is my problem. I calculate second derivative, okay? And that's it. Okay, so of course, if lambda, because I'm using the second derivative, second order, my null space is linear, okay? So if lambda is really large, I penalize a lot the acceleration. What do I get? A line, okay? If I don't penalize anything, I will try to interpolate the data. So I have to choose lambda to get the shape right, okay? So what I'm doing now, just to show you, now the number of bases is fixed. What is changing is lambda. Okay, so the larger lambda is, the closer to a straight line I'm getting. Okay, so that's what this is showing. I mean, what we have here is just the product of each basis multiplied by the coefficient. Okay, so that's what you are getting. Anyway, so of course, I am in general interested on uncertainty quantification. I will give you what I believe my true curve is, but I have to give you how sure I am about this, okay? And that goes through, okay, assuming something about your error. Depending on the type of data, the assumption about the error is going to be different, okay? For example, if I'm in, suppose that I want to predict the spatial, I have data about temperatures in Spain, okay? And I want to show you what the map of the temperatures is, okay? My uncertainty will be somehow spatially related, okay? Because two locations close to each other are going to have similar temperatures. So I will assume a particular distribution for the error there, okay? But if you want to quantify uncertainty, you have to go through assuming some sort of distribution for your error, okay? So once you assume something, okay, the basic thing, of course, is that you assume that your errors are independent, normally distributed, okay? This would be the basic thing. But the nice thing is, well, then you have to get away from least squares. Least square doesn't tell you anything about any error, but you move to likelihood, okay? And then the maximum likelihood will allow you to estimate the variance of the error, okay? So the nice thing about this, and Alex showed it, is that the penalty induces a covariance structure on the spline coefficients, and this translates, okay, to uncertainty on your function. So I think this is too small, but if you could, there is a gray band around the, it's just too light, but there is a band around the function that is giving me the uncertainty that I have about this. What I'm saying, with a very high probability, on average, my true function is going to be within that band, okay? And that is the power of the statistical model, okay? It's not approximation only. I'm giving you an approximation with a certain measure of uncertainty, okay? Yes. That is smooth. F, I'm going to represent F as the sum of, here. Okay, here we go. You assume that F can be represented as the product of bases multiply, that you have a smooth representation, your true function is smooth somehow.
Good uniform approximation.
Yeah, exactly. This is, as I was saying, this is not useful for everything, okay? But if you believe that what you have is this, then you go along. So what do you do in 2 dimensions? There you go, tensor product. We have been listening to this week. This is what, well, this is not a true representation of a B-spline tensor product of B-splines because they will overlap, okay? I put it like, this is like the carton where you put the eggs, upside down, okay? But they will overlap, but I didn't overlap them because otherwise you don't see anything, okay? So this is your basis, and your coefficients, let's say, are located here. They are on a matrix now, okay? My coefficients. So how do I control the shape now if I don't want to choose the knots? Well, I'm going to penalize this. I have a grid of knots, okay? And I'm going to penalize, I'm going to calculate penalties on one direction, and I'm going to sum them, and then on the other direction, okay? And I'm going to sum them, but I'm going to allow to have a different degree of smoothness in each direction. This is something very important. I have a non-isotropic penalty, okay? I have a smoothing parameter controlling one direction and another smoothing parameter on the other direction, but all coefficients are penalized in both directions. You can, do a diagonal penalty if you believe your process. For example, I work with mortality data, mortality tables, which give you how many people die per year and age, and you have cohort effects. You can add that type of penalty here, okay? So this is something very, very important when you are working in situations in which your covariates have different units, okay? It wouldn't make sense to penalize in the same way something measured in Celsius degrees and something measured in kilometers, okay? So you need to be able to separate this amount of smoothing. This is just an example, okay? And this is a paper we wrote in 2026. And if you have data on regular grids, we present here an incredibly fast way to solve penalized least square without having to calculate the tensor product, okay? When you have data on, like, imagine MRI, you have images a long time, you have a cube, okay? So if you want to smooth that, okay, you don't need to calculate the 3-dimensional tensor, okay? You work with each dimension and then you rotate, okay? So this is extremely fast. So this is a case in which we have an image with noise, okay? And then we extract the signal from the noise, okay? And as I said, this is done very, very, very fast. Okay, so sometimes, of course, when you work with tensor products, the number of coefficients increases a lot, okay? And sometimes this can become computationally, difficult. Sorry. Oh. What did I do? Okay. Can become, if you have a d-dimensional problem and you have k knots per dimension, you have k to the power of d coefficients, okay? This is complicated. And also, in many situations, there is no way you can explain anyone what a k-dimensional function is. In my setting, it's not only important to estimate the function, but to explain what is going on, okay? So what can we do? Maybe we can explain this k-dimensional function as the sum of lower dimensional functions, which will save us computational time, but will also allow us to explain what is going on. I'll give you an example. Some data I worked with some years ago. Pollution in Europe, okay, over the years. We have the map of Europe and we have observations of ozone at ground level, okay, which is what the cars give you, okay, essentially. So this is a three-dimensional problem. I have the latitude and longitude of the point where I collect the data and over time. If I give people this a three-dimensional function, the environmentalists, they don't understand what is going on. Maybe they want to see the sum of things, a pure effect of time, where this thing is going with time for every point in Europe. What would be the average map over the years? And something that, in fact, yes, is three-dimensional. But decomposing your function will allow you also to explain what is going on. And this is what I propose. Okay, decomposing a two-dimensional function as a sum of two one-dimensional is too simple. Okay, this is not going to work. Okay, but okay, you can decompose it in this way. This is related to the last talk that we saw yesterday. I can assume that my two-dimensional is the sum of something in one dimension, something in another dimension, and something that cannot be explained as univariate functions, okay? But you are going to tell me, Maria, then you have even more parameters than now, because you again have here the two-dimensional thing, okay? So you are increasing. No, because what are we going to assume? That because we have taken part of the shape of my function here, I can reduce the dimension here, okay? Imagine that here I have 20 knots, 25 knots per dimension, okay? 625. And now I say, okay, I'm going to use a function with 25, 25, and then 7 by 7. What is left to explain, I reduce the dimension. So I save a lot of points. What do I have? Okay, I have a B-spline representation of my function, univariate, the univariate, and the bivariate. And then I have a penalty for the univariate, the other penalty, and the penalty for the bivariate. But this is the key point. So I want to have this type of thing, okay? The two-dimensional thing I decompose in 3 parts, but I reduce the dimension of the last one, okay? And how do I do that? In any way I want? No, not in any way I want. And I bring you the idea that we've been learning about this, the nested B-spline basis, okay? So I want that my function, the span, is the same, okay? So I use a basis for the one-dimensional, I use a basis for the other one, and instead of calculating the tensor product of those two, I calculate the tensor product of a reduced basis, okay? And how do I choose the reduced basis so the span, of the whole function remains intact, okay? I choose the knots of the interaction. I'm going to be a division of the knots of the original basis. I'll show you with a plot, okay? This is a large B-spline basis. The middle one is a nested basis within the one there, and I put the two ones together. So you see that the space spanning by both is the same, but I reduce the number of coefficients, okay? And I'll give you an example. I simulated some data, which is on the top left, okay? I put this through surface, and then I added a noise. And I estimated this true surface in two different ways, okay? Using a full tensor with 625 knots, 25 per dimension, or as the sum of three components. In total, only 97, okay, coefficients. And my full surface is the sum of these three things, okay? One dimension, and the tensor product, okay? But reduced tensor product. And I'll show you, okay? I calculated the distance between what I observe, okay? I get less error with less coefficients, okay? It won't be always the case, okay? But yes. Oh, okay, of course. You have, yeah, I put constraints on the coefficients. For example, for the one-dimensional, I assume that the sum of the coefficients is 0, which is the same as assuming the mean of the one-dimensional function is 0. For the two-dimensional function, I assume my coefficients are on a matrix, the sum per row and per column, the same type of constraints as in ANOVA factorial analysis, exactly the same. Then you guarantee identifiability. But the other key point about the identifiability is that the basis for the interaction is nested for the basis of the main effects. Otherwise, you cannot guarantee the identifiability. Okay, I use this one, okay? So as you can see, the space span is the same as the one-dimensional one, okay? So what I'm taking here is I divide it by 2 the number of knots, and I put them in the same positions as the original ones, but half of them. This is the small one.
Yeah, how about the middle one? The middle one, the last one, the middle one.
Oh, because here at the knots they are the same. This one is the same as this one. I'm not sure if I understand your question. Yeah, yeah. It is the same. I mean, it's just because I put the two of them together, it looks like they are different. No. I mean, the top one is the gray one here. Yeah? Yeah, for the one-dimensional. Oh, I only use the middle one. I only should, yeah, exactly. And okay, I need to go quickly because so what I wanted to show you is that, you can get really decomposing, okay, with less coefficient or knots, you can get even better, okay, because it's much more flexible, okay? So although I have many more things to say, I want to talk about this because the elephant in the room is how do we choose lambda, okay? In my models, I have many penalties because I use penalties for a lot of things. So the traditional way is cross-validation, generalized cross-validation. Okay, if you have 1 or 2-dimensional problem, this is okay. But if you have a 10-dimensional problem, which is very common in data analysis, there is no way you are going to work on a grid, okay? So one possibility, okay, and this is a paper in 2017, is that you go Bayesian, okay, which is partly related to what Alex says, okay? So what I'm going to assume is that my coefficients, the spline coefficients, are random, okay, with a certain particular covariance structure, And the covariance structure is the inverse of the penalty multiplied by a variance parameter. What is the beauty of this? First, that if of course, I'm in the likelihood setting, okay? If I calculate, I have a joint distribution for my response and my coefficients. And then I have a marginal likelihood. The marginal likelihood is exactly the penalized least squares, okay? But the beauty is that the smoothing parameter has a meaning, has some meaning now. It's the ratio between the error in the data divided by the variability of my coefficients. If my coefficients have variance 0, all of them are 0, okay? I have a straight line, and lambda is infinity, very large lambda. If the small, the larger the variance of my coefficients, okay, the smaller lambda is, the more wiggly my curve is. The beauty of this is that I have one optimization problem in which I estimate lambda and the coefficients at the same time. Okay, I iterate between estimating the lambdas and estimating the coefficients. This is extremely fast. You can estimate 80 smoothing parameters in 10 seconds. Okay, so it's very, very, very fast because it's within, the iterative reweighted least squares that, is very well known. So this is very, very important. So you estimate, you update lambda, then you repeat, and so on. This is implemented in many, in the MGCB package by Simon Booth, in R. There is another package called separation of overlapping penalties. This is implemented. If you want to try it out, it's implemented in many, many places. And I want to show you one thing, okay, just to finish. What happens when I have data like this? Okay, this is a pain, okay, because it's not uniformly smooth everywhere, okay? So you can undersmooth, okay? If lambda is very small, then you undersmooth, okay? If you put, if lambda is very large. If lambda is very small, okay, but you get these like ripples here that they are not true. So what can you do? Instead of having one lambda that controls the difference between the coefficients, you can have one lambda for each difference between the coefficients. So you have the sum, of a lot of penalties. Okay, so you adapt your smoothness as you move along. Okay, and then you get something like this, which is what you would expect. Okay, so it has some computational cost, but as I said, you can do this nowadays in a very, very, very fast way. Okay, so idea. The power of 1,000 knots is the discipline of a single penalty. And you can impose a lot of information, prior information that you have using penalties. If you know that your curve is increasing, is convex, you can impose that through your penalties. So if you have this type of problems, try using penalized splines. So thank you very much.